By the late summer of 1943, the strategic equilibrium of the Second World War had shifted irrevocably. The Allied powers, having secured North Africa and successfully invaded Sicily, were now staring across the English Channel at the ultimate prize and the ultimate obstacle, the invasion of Northwest Europe. However, between the cliffs of Dover and the liberation of Berlin lay a monolithic engineering challenge that defied all conventional military solutions. Adolf Hitler, aware that the Second Front was inevitable, had decreed the construction of the Atlantic Wall. This was not merely a propaganda term. It was a physical reality of staggering proportions. Stretching nearly 2,000 miles from the Arctic border of Norway down to the Spanish frontier, it consumed millions of tons of concrete and steel, diverting resources that were desperately needed on the Eastern Front. The German defensive doctrine, engineered by the organization taught and refined by Field Marshal Erwin Rommel, was predicated on a single, brutal axiom. The enemy must be destroyed at the water's edge. Rommel knew that if the Allies established a beachhead and unloaded their heavy armor, the war was lost. Therefore, the defense was concentrated on the beaches themselves. The coastline was transformed into a lethal geometry of interlocking fire zones. The resistance nests, Widerstands Nester, were bunkers of reinforced concrete, capable of withstanding direct hits from naval artillery and aerial bombardment. They were positioned to create overlapping fields of machine gun and anti-tank fire that would turn the intertidal zone, the sand between the low and high water marks, into a slaughterhouse. But the most formidable component of this defense was not the gun, but the wall itself. German engineers had constructed massive anti-tank walls directly behind the shingle of the most likely invasion beaches. These were not simple barricades. They were feats of brutalist civil engineering, standing 10 feet, 3 meters high, and often 7 feet, 2 meters thick. These walls were constructed of high-grade reinforced concrete. They were designed specifically to stop a tank dead in its tracks. A Churchill or Sherman tank, struggling through the soft sand and under heavy fire, would reach the top of the beach only to find an impassable vertical slab of concrete. Trapped against this wall, unable to advance and unable to retreat into the sea, the tank would become a stationary target for the 88mm anti-tank guns positioned on the flanks. The Allied planners at Cossack, Chief of Staff to the Supreme Allied Commander, faced a crisis of physics and logistics. To succeed on D-Day, they needed to breach these walls within minutes of the first wave landing. If the walls remained intact for even an hour, the landing beaches would become congested choke points, and the invasion force would be annihilated by German artillery zeroed in on the sand. The conventional solutions were examined and discarded one by one. Naval gunfire. The great battleships could hurl 16-inch shells, but their trajectory was flat. Hitting a 10-foot wall hidden behind a dune from 5 miles out at sea required a precision that was mathematically impossible in combat conditions. A near miss would simply churn the sand. A direct hit might only chip the concrete. Aerial bombardment. Heavy bombers like the B-17 and Lancaster were area weapons. To guarantee a breach in a specific section of wall, they would have to carpet bomb the entire coastline, creating a lunar landscape of craters that would be impassable to Allied tanks. Precision dive bombing was too risky against the dense flak concentrations. Combat engineers, sappers. Sending men forward on foot with satchel charges was suicide. The amount of explosive required to breach a 10-foot thick wall was immense. Hundreds of pounds of TNT. A sapper carrying a 20-pound charge could scratch the surface, but he could not demolish the structure. To breach the wall, they needed to deliver 1 ton, 2,000 lbs of high explosives to a precise point at the base of the wall, instantly. This requirement created a technological paradox. The delivery system had to be unmanned to save lives, armored to survive the approach, capable of traversing soft sand and barbed wire obstacles, and powerful enough to carry a payload equivalent to a blockbuster bomb. It had to do all this while being launched from a landing craft that was itself bobbing in the surf. No vehicle in the Allied inventory could do this. A tank loaded with explosives was too slow and too valuable. A rocket-propelled sled would get stuck in the dunes. The desperation in the British Admiralty was palpable. The planners realized that standard military engineering had reached its limit. They needed lateral thinking. They needed a solution that ignored the rule book. In this climate of high-stakes anxiety, the problem was handed down from the serious men in Whitehall to a small, secretive, and eccentric department known as the Directorate of Miscellaneous Weapon Development, DMWD. The DMWD, based in the requisitioned offices of the Admiralty, was a collection of scientists, reserve officers, writers, and engineering mavericks who were colloquially known as the Wheezers and Dodgers. They were the department of last resort and the Q branch of the real world. Led by the visionary and occasionally reckless Captain Charles Goodeve and featuring the brilliant aeronautical engineer and novelist Neville Shute Norway, the DMWD specialized in the unorthodox. They had already developed the Hedgehog anti-submarine mortar, a success, and the vertical cable barrage, a mixed success. They thrived on the fringes of physics. When the problem of the Atlantic Wall landed on their desks, the DMWD engineers did not look at tanks or cannons. They looked at the fundamental principles of motion. They reasoned that a wheeled vehicle gets bogged down because its weight pushes it into the sand. But what if the vehicle was all wheel? What if the explosive payload was the axle itself? The concept that emerged from their brainstorming sessions was radical, geometric, and bordering on the insane. They envisioned two gigantic steel wheels, each 10 feet in diameter, connected by a central drum filled with 4,000 pounds of TNT. To propel this monster, they rejected internal combustion engines, too heavy, too complex, and electric motors, too weak. They turned to the rawest form of propulsion available: rockets. By attaching banks of cordite rockets to the rims of the giant wheels, they could spin the device up to terrified speeds, projected to be over 60 miles per hour. The centrifugal force would, theoretically, keep it upright like a giant gyroscope. The momentum of a 10-ton spinning steel bobbin would allow it to crush barbed wire, smash through timber obstacles, and roll inexorably up the beach until it slammed into the concrete wall. Upon impact, a fuse would trigger the central drum, vaporizing the wall and opening the road to France. They named it the Great Panjandrum. The name was taken from an 18th century nonsense poem by Samuel Foote. And there were present the pickaninnies, and the job-lilies, and the garayulis, and the Grand Panjandrum himself, with the little round button at top. It was a fitting title for a weapon that seemed to have rolled out of a fever dream. It was not just a weapon. It was a rolling declaration that the British Empire was willing to try absolutely anything to win the war. The Wheezers and Dodgers began drafting the blueprints for a machine that would become the most spectacular failure in the history of military engineering. The transition of the Great Panjandrum from a sketches on a DMWD notepad to a physical reality took place not in a high-tech military laboratory, but in the gritty industrial district of Leytonstone, East London. The contract for the prototype's construction was awarded to a civilian engineering firm, a company whose workers were more accustomed to riveting boilers, assembling bridge girders, and repairing heavy industrial cisterns than building experimental siege engines for the Royal Navy. When the blueprints arrived, stamped with the highest classification of secrecy, the shop foremen stared at them in bewildered silence. They were being asked to build a machine that defied every convention of their trade. It had no engine, no cockpit, no tracks, and no apparent method of control. It was, in essence, a giant rolling bobbin of death. The specifications were colossal. The primary structure consisted of two enormous steel wheels, each measuring 10 feet, 3 meters in diameter. These were not delicate spoked wheels like those of a bicycle or a carriage. They were solid, heavy discs of plate steel, reinforced with a complex lattice of internal bracing designed to withstand immense centrifugal forces. The rim of each wheel was a foot wide, a band of steel intended to crush barbed wire, sand dunes, and bone alike. Connecting these two titans was the central payload drum, a massive cylinder designed to house 4,000 pounds, 1/800 coers of high explosives. In the final combat version, this drum would be packed with amytal or TNT. For the prototype being built in Leytonstone, it was filled with an equivalent weight of dry sand. The engineering challenge facing the civilian workers was not just structural, it was kinetic. The entire assembly weighed nearly 10 tons. For the device to work, it had to roll true. If the central drum was welded even a fraction of an inch off center, or if the wheels were not perfectly parallel, the device would develop a catastrophic wobble. At the projected speed of 60 miles per hour, a wobble of that magnitude would tear the machine apart before it ever reached the Atlantic Wall. The workers labored under the constant pressure of the Admiralty, aligning massive steel plates with micrometers and sledgehammers, trying to impose precision on a design that was inherently brutal. But the true heart of the Panjandrum, and the source of its future infamy, was its propulsion system. The DMWD engineers, led by Neville Shute Norway, had calculated that to accelerate a 10-ton dead weight through soft beach sand and over obstacles, they needed massive, instantaneous thrust. Internal combustion engines were too heavy and complex. Electric motors were too weak. The solution was cordite rockets. Specifically, the 3-inch unrotated projectile, UP, a standard anti-aircraft rocket modified for horizontal thrust. The rim of each steel wheel was fitted with mounting brackets for the rockets. The design called for a staggering battery of 70 rockets, 35 on each wheel. They were arranged tangentially along the rim, like the fireworks on a giant Catherine wheel. The firing sequence was a nightmare of electrical engineering. The rockets could not all be fired at once. The initial torque would simply spin the wheels in place, digging a trench in the sand. Instead, they had to be fired in stages. A primary bank of rockets would ignite to start the rotation and overcome static inertia. Then, as the wheel gathered speed, centrifugal switches and timers would trigger secondary and tertiary banks of rockets to maintain acceleration and overcome the drag of the sand. This required a complex web of electrical wiring to be threaded through the spinning wheels. The spaghetti of copper wires had to be robust enough to survive the violent vibration of a steel wheel hammering over rocks, yet flexible enough not to snap under the G-forces of rotation. The Leytonstone electricians found themselves soldering connections on a machine that looked like a steampunk fantasy. A single loose connection, a short circuit caused by salt water or sand, or a battery failure would mean uneven thrust. If the rockets on the left wheel fired with just 10% more force than the rockets on the right wheel, the Panjandrum would not roll straight. It would turn. And since the device had no steering wheel, no brakes, and no pilot, a turn meant it would become an unstoppable, rocket-powered juggernaut seeking its own target on the beach. As the prototype neared completion, it took on a terrifying, gargantuan presence in the workshop. Standing 10 feet tall, smelling of welding flux and grease, it dominated the floor. It looked less like a weapon of the 20th century and more like a rejected siege engine from the Middle Ages, updated with high explosives. The workers nicknamed it the Drum, but among the DMWD officers who visited to inspect the progress, the anxiety was palpable. They were looking at a machine that relied on the perfect synchronization of 70 unstable cordite rockets to move in a straight line. They knew the physics of gyroscopes, and they knew the unpredictability of solid fuel. They were building a monster, and they were about to take it off the leash. The location selected for the inaugural trial of the Great Panjandrum was the beach at Westward Ho in North Devon. This site was not chosen for its picturesque name or its status as a Victorian seaside resort. It was selected for its precise geological similarity to the target beaches of Normandy and the Pas de Calais. It featured a long, flat expanse of firm sand exposed at low tide, backed by a unique geological feature, the Pebble Ridge. This massive, natural bank of smooth gray stones offered a ready-made observation platform for VIPs and a modicum of blast protection for the nearby Royal North Devon Golf Club, the oldest golf course in England. In September 1943, the Directorate of Miscellaneous Weapon Development, DMWD, descended upon this quiet coast, effectively annexing it for the war effort. The arrival of the DMWD was a spectacle of chaotic secrecy. Convoys of canvas-covered trucks navigated the narrow Devon lanes, carrying equipment marked Top Secret. The beach was cordoned off with miles of barbed wire and signs warning of danger, unexploded ordnance. Although the locals, accustomed to the eccentricities of wartime training, quickly gathered on the dunes to watch the Navy's funny business. The Panjandrum itself arrived in sections, too large to be transported whole. It had to be reassembled directly on the sand, a process that required cranes, gantries, and a team of engineers fighting against the tide tables. As the device took shape on the beach, its scale became truly apparent against the open horizon. Standing 10 feet high, the steel wheels looked like the remnants of a destroyed factory. The central drum, for this initial trial, was filled not with high explosives, but with 4,000 pounds of sand to simulate the combat weight, without the risk of vaporizing the county of Devon. The rim of each wheel was fitted with a modest initial battery of 18 cordite rockets, enough to test propulsion and stability without achieving lethal velocity. The atmosphere on the beach was a strange mix of scientific rigor and carnival anticipation. Neville Shute Norway, the project's chief calculator, paced the sand, checking the tide lines and the density of the surface. He knew that the coefficient of friction on sand was a variable that changed with every wave. A wet patch offered different resistance than a dry patch. The Panjandrum had no suspension, no steering, and no pilot to correct for these variables. It relied entirely on the brute force of momentum and the theoretical stability of gyroscopic action. The engineers retreated to a concrete observation bunker reinforced with sandbags. A gathering of senior officers from the Army and Navy stood on the Pebble Ridge, binoculars raised, expecting to see the future of amphibious warfare. The seagulls wheeled overhead, and the Atlantic wind whistled through the steel spokes of the machine. The stage was set for a confrontation between Newtonian physics and British optimism. On the morning of September 7, 1943, the tide receded to reveal a mile of pristine, wet sand. The Panjandrum stood alone, a dark monolith casting a long shadow. A firing cable snaked from the hub across the beach to the bunker. The countdown began. The order to fire was given. The electrical circuit closed. The result was spectacular, but not in the way the engineers had hoped. The first bank of rockets ignited with a deafening, tearing roar that sounded like a canvas sky being ripped apart. Smoke billowed instantly, obscuring the machine in a dense cordite fog. Then, slowly, majestically, the Panjandrum emerged from the cloud. It began to roll. For the first 50 yards, it seemed to vindicate its creators. It moved straight, gathering speed, its steel wheels biting into the sand, throwing up rooster tails of water and grit. A cheer went up from the observers. It was working. It was a rolling wall of fire heading for the target line. But then, the unforgiving reality of the beach intervened. The surface was not uniform. The right wheel encountered a patch of slightly softer, wetter sand, a soft spot common to intertidal zones where water lingers beneath the surface. The increased friction caused a momentary drag on the right side. In a vehicle with a driver and a steering wheel, this would be a minor correction. In the Panjandrum, which relied entirely on differential thrust and momentum, it was catastrophic. The drag on the right wheel caused it to slow down by a fraction. The left wheel, its rocket still firing at full thrust, continued at full speed. The result was instantaneous torque. The Panjandrum did not just veer. It pirouetted. It violently twisted to the right, carving a deep, curved furrow in the beach. As it turned, the centrifugal force confused the crude rocket ignition timers. Rockets that should have fired later fired now. Rockets that should have been firing horizontally to push the wheel forward were now, due to the lean of the machine, firing vertically into the sand or up into the air. The device became a chaotic, spinning firework display. It wobbled, leaned over precariously, and then, with a final burst of rocket thrust, tipped onto its side. It lay there, spinning maniacally in the sand like a dying coin, rockets flailing and exploding in all directions, digging a crater in the beach and sending shrapnel whistling over the heads of the terrified seagulls. The generals lowered their binoculars in silence. The DMWD engineers put their heads in their hands. The Panjandrum had traveled about 200 yards, but it had ended up facing back towards the sea. It had proven it could move. Now it just had to prove it could go where it was told. The Weezers and Dodgers realized that raw power was not enough. They needed control. And their solution to this problem would lead directly to the next, even greater disaster. Following the humiliating failure of the initial tests at Westward Ho, the engineers of the Directorate of Miscellaneous Weapon Development, DMWD, retreated to their bunkers in a state of frantic introspection. The physics of the Panjandrum had proven wildly unstable. The slightest irregularity in the sand caused one wheel to bite harder than the other, creating instantaneous, uncontrollable torque that sent the massive explosive drum careening off course. With the invasion of Europe looming, the pressure from the Admiralty was immense. They needed a wall-breaching weapon, and they needed it to drive straight. The solution proposed by Neville Shute Norway and his team was a classic example of engineering by addition, trying to solve a fundamental flaw by bolting on more complexity. They theorized that the device lacked directional stability because it had only 2 points of contact with the ground. Their answer was to turn the bicycle into a tricycle. They designed a third wheel, a steerable, non-powered guide wheel to be attached to the center of the explosive drum via a rigid trailing arm. This third wheel was intended to act as a rudder, anchoring the device to a linear path and resisting the violent yawing forces generated by the uneven rocket thrust. To control this wheel, a system of steel cables was rigged, theoretically allowing fine adjustments to the course. However, the addition of the third wheel introduced a new set of catastrophic variables that the engineers, in their desperation, failed to model correctly. The beach at Westward Ho was not a smooth laboratory floor. It was a dynamic, undulating surface of wet sand, shingle, and mud. When the modified Panjandrum was tested, the third wheel did not act as a stabilizer. It acted as a chaotic fulcrum. If the third wheel hit a soft patch of sand, it dragged, acting as a brake that destabilized the entire assembly. If it hit a rock, it bounced violently, transmitting shock waves through the central drum that disrupted the delicate electrical firing timers of the rockets. The rudder became an anchor, dragging the beast into unpredictable spins. Furthermore, the added weight and drags of the third wheel required more power. The DMWD responded by increasing the number of rockets on the main wheels from roughly 40 to over 70. This increase in raw thrust amplified the violence of the rotation. When the rockets ignited, the torque was now so immense that it twisted the frame itself. The Panjandrum was no longer just rolling, it was vibrating with the energy of a contained explosion. The date was January 1944. The dress rehearsal for the invasion of Europe was underway, and the DMWD had summoned the elite of the Allied command to Westward Ho for the definitive demonstration of the Great Panjandrum. The audience assembled on the pebble ridge overlooking the beach was a who's who of the war effort. Admirals, generals, scientific advisors, and most notably, the official photographer Clementaski, who set up his tripod dangerously close to the waterline to capture the historic moment. The mood was tense, the wind was whipping off the Atlantic, and the gray sky promised rain. The Panjandrum sat on the sand, fully loaded. This was the final mark. Equipped with the third wheel, reinforced bracing, and a full battery of live cordite rockets. It looked less like a weapon and more like an instrument of industrial torture. The order to fire was given. What followed is widely considered the most spectacular and hilarious failure in the history of military engineering. The first bank of rockets ignited with a thunderous roar. The wheels began to turn, throwing up great roosters' tails of wet sand. The Panjandrum accelerated, gathering momentum, moving straight for the target line. For a few glorious seconds, it seemed to work. Then, chaos took the wheel. A clamp holding a battery of rockets on the right wheel failed under the centrifugal load. A cluster of live, screaming rockets broke loose, spinning wildly across the beach like angry serpents. The loss of thrust on the right side caused the Panjandrum to execute a violent, high-speed turn to the right, directly toward the VIP observation gallery. The massive rolling bomb, now wreathed in smoke and spitting flames from its remaining rockets, charged the pebble ridge. The scene descended into absolute pandemonium. Distinguished admirals and generals, forgetting their dignity, dived for cover behind the shingle wall or scrambled up the dunes in panic. Clementaski, the photographer, realized too late that he was in the direct path of the beast. He abandoned his camera and ran for his life as the 10-foot steel wheels thundered past him, missing him by mere feet. Adding to the absurdity, a local dog, excited by the noise and the chasing figures, ran onto the beach and began to bark at and chase the flaming, rolling monster, nipping at its wheels as it careened towards the sea. The Panjandrum, having terrified the high command, finally lost its momentum. It wobbled, tipped over, and crashed into the surf, sizzling and exploding in a cloud of steam and cordite. The silence that followed was broken only by the sound of the waves and the heavy breathing of the generals lying in the sand. The verdict was immediate and absolute. The Great Panjandrum was dead. It was not a weapon. It was a hazard to its own side. The project was scrapped on the spot, leaving behind nothing but a crater in the sand and a story that would be whispered with laughter in the Admiralty for decades. From a modern engineering perspective, the failure of the Great Panjandrum at Westward Ho was not an accident. It was a mathematical inevitability rooted in the unforgiving laws of dynamics. The DMWD engineers had bet everything on the principle of gyroscopic stability. The idea that two massive, spinning wheels would naturally resist turning, keeping the device on a straight path like a giant, rolling coin. In a vacuum, or on a perfectly smooth surface with perfectly synchronized propulsion, this might have worked. But on a British beach, it was a fallacy. The primary culprit was differential thrust. The Panjandrum was powered by banks of cordite rockets. Cordite is a solid propellant that burns at a rate determined by its chemical composition, grain size, and temperature. No two rockets burned exactly alike. In a salvo of 35 rockets on one wheel, statistical variances meant that the total thrust vector was never perfectly constant. At any given millisecond, the left wheel might be producing 5% more thrust than the right. In a vehicle with a steering system, a driver corrects this yaw instantly. In the Panjandrum, which had no driver and no steering, this differential thrust created a turning moment. Once the turn began, the gyroscopic forces that were supposed to stabilize the device actually worked against it. Due to a phenomenon known as precession, a force applied to a spinning gyroscope manifests 90 degrees later in the rotation. The uneven thrust didn't just push the wheel, it twisted the frame. This torque load was transmitted to the central axle, the explosive drum. The lack of a suspension system meant that every ripple in the sand, every pebble, and every change in surface density transmitted a shock wave directly into the rigid steel structure. These vibrations loosened the electrical connections of the rocket igniters, causing misfires that further unbalanced the thrust. The Panjandrum was trapped in a feedback loop of instability. The faster it went, the more violently it vibrated, and the more erratic the propulsion became. It was a machine designed to fight the laws of physics, and physics won every time. In the decades following the war, a compelling and persistent theory emerged among military historians and analysts. What if the Panjandrum was never meant to work? What if the entire project, the public tests on open beaches, the ridiculous design, the spectacular failures witnessed by civilians and spies, was a calculated piece of theater designed to be seen by the enemy? This theory connects the Panjandrum directly to Operation Fortitude, the massive Allied deception campaign designed to convince the German High Command that the invasion of Europe would target the Pas de Calais rather than Normandy. The logic is sound. The beaches of the Pas de Calais were heavily fortified with massive concrete anti-tank walls, the exact obstacle the Panjandrum was ostensibly designed to breach. Normandy, by contrast, relied more on beach obstacles and terrain. By pouring visible resources into a dedicated wall-breaching weapon, the British were sending a loud, clear signal to Berlin. We are preparing to attack your strongest walls. The leaking of the Panjandrum tests supports this hypothesis. Westward Ho was a restricted area, but it was not invisible. German reconnaissance aircraft flying high-altitude sorties or local sympathizers could easily observe the massive, loud, fire-spitting wheels burning up the beach. The spectacle was too loud to be a true secret. If the Germans saw the British testing such a device, it reinforced their belief that the attack was coming at the Pas de Calais. If this theory is true, then the Great Panjandrum was the most expensive, dangerous, and hilarious prop in military history. A weapon designed to fail spectacularly in order to sell a lie. The laughter of the generals on the beach might have been part of the script, a grim chuckle at the expense of the Abwehr analysts trying to interpret the purpose of a flaming, rolling wheel. Despite the humiliating and public failure of the Panjandrum, the Directorate of Miscellaneous Weapon Development, DMWD, proved to be one of the most valuable, if eccentric, assets of the Allied war effort. The Panjandrum was merely the most visible failure in a portfolio of brilliant successes. The same team of Weasers and Dodgers that built the rocket wheel also developed the Hedgehog anti-submarine mortar. Unlike depth charges, which exploded at a set depth and often allowed U-boats to escape during the death period of the explosion, the Hedgehog fired a circular pattern of contact-fused spigot mortars ahead of the ship. They only exploded if they hit the submarine. It increased the kill rate of British escorts dramatically and was a key factor in winning the Battle of the Atlantic. They also developed the Mulberry Harbors, the massive floating concrete ports that were towed across the Channel on D-Day. When the captured French ports were sabotaged by the Germans, the Mulberries allowed the Allies to offload the heavy armor and supplies needed to sustain the invasion. The engineering daring required to conceive of floating concrete caissons was born from the same uninhibited mindset that produced the Panjandrum. The DMWD operated without the fear of embarrassment. They understood that in a war of national survival, for every 10 ridiculous failures, there might be one war-winning success. The Panjandrum was the price paid for the Hedgehog and the Mulberry. It stands as a monument to the uninhibited, desperate creativity of a nation with its back to the wall. The technological lineage of the Panjandrum did not end in the surf at Westward Ho. The data gathered on solid-fuel rocketry and the behavior of large projectiles in ground effect proved invaluable for the development of later, more practical weapons. The Churchill AVRE, Armored Vehicle Royal Engineers, which landed on D-Day, carried a weapon known as the petard mortar, a dustbin-sized projectile designed to smash concrete bunkers. While not a rolling wheel, its mission was the same, delivering a massive explosive charge to a hard target at close range. The Panjandrum's failure reinforced the idea that specialized armored vehicles, not autonomous gadgets, were the solution to beach fortifications. Furthermore, the spirit of the Panjandrum, the willingness to use rockets for ground propulsion, lived on in the Sherman Tulip, tanks fitted with aircraft rockets, and the land mattress rocket artillery systems used in the final crossing of the Rhine. The experiments at Westward Ho taught British engineers valuable lessons about stability, ignition sequencing, and the sheer power of cordite. The Great Panjandrum became a byword for a magnificent failure. But the men who built it went on to engineer the victory in Europe. The wheels stopped rolling, but the momentum of innovation it generated helped smash the Atlantic Wall in June 1944, just not in the way they originally intended. The humiliating public failure of the Great Panjandrum at Westward Ho did not signal the end of the British effort to breach the Atlantic Wall. Rather, it signaled a critical pivot in engineering philosophy. The Admiralty and the War Office recognized that the fundamental concept of the Panjandrum, an autonomous, unguided, rocket-powered device, was fatally flawed due to its lack of control. The beach environment was too chaotic for a machine that could not think or be steered. The solution, they realized, lay not in reinventing the wheel, but in modifying the tank. This realization led directly to the empowerment of Major General Percy Hobart and the creation of the 79th Armored Division, a unit entirely dedicated to specialized armored warfare. Hobart, an eccentric and brilliant engineer who had been forced into retirement before the war due to his unconventional ideas, was brought back by Winston Churchill himself. He looked at the problem of the concrete wall and applied a pragmatic solution. Instead of sending a rolling bomb, send a tank carrying a demolition charge. The spiritual successor to the Panjandrum was the Churchill Avri, Armored Vehicle Royal Engineers. This was a heavy Churchill tank modified to carry a specialized weapon known as the petard mortar. The petard was a short-barreled 290mm spigot mortar that fired a 40-pound explosive projectile nicknamed the Flying Dustbin. It was not a long-range weapon. Its effective range was only 80 yards. But like the Panjandrum, it delivered a massive, crushing explosive charge directly to the face of a concrete fortification. Unlike the Panjandrum, the delivery system, the tank, was armored, steerable, and could traverse any terrain. The failure of the rocket wheel had cleared the intellectual space for the success of the combat engineer tank. The funnies that stormed Normandy, the flail tanks, the bridge layers, the bunker busters, were the rational, controlled evolution of the desperate creativity that had birthed the Panjandrum. On the morning of June 6, 1944, the theories of the DMWD were finally put to the test on the beaches of Normandy. While the Panjandrum was absent, its spirit was present in the sheer violence of the assault on the fortifications. The Atlantic Wall was real, and it was formidable. On Sword and Juno beaches, the British and Canadian forces encountered the concrete anti-tank walls that had haunted the planners for years. The solution was a combination of brute force and courage. The Churchill Avries waded through the surf, their petard mortars traversing to find targets. They pulled up to within point-blank range of the concrete bunkers and walls. With a dull thud, the Flying Dustbins were launched, somersaulting through the air to smash against the German concrete. The explosions were devastating, cracking the structures and concussing the defenders inside. Where the walls were too thick, teams of Royal Engineers, men who had trained with the same urgency as the Panjandrum team, ran forward under fire to place General Wade charges by hand. The breaching of the Atlantic Wall was not the clean, automated destruction envisioned by the creators of the Panjandrum. It was a messy, bloody, and mechanical grind. But it succeeded. By the end of D-Day, gaps had been blown in the sea walls and the Allied armor was pushing inland. The Panjandrum had promised a miracle. The AVREs and the engineers delivered a reality forged in steel and high explosives. The lesson was clear. In the chaos of the beachhead, reliability is worth more than raw power. What happened to the physical remains of the Great Panjandrum? After the disastrous final test in January 1944, the wreckage was largely abandoned on the beach at Westward Ho. The steel wheels, twisted and blasted by the erratic rockets, were eventually hauled away for scrap. Metal was too precious to leave rusting in the sand. However, local legends persist that fragments of the device, perhaps even one of the massive hubs or a section of the axle, remain buried deep in the shifting sands of the Pebble Ridge. In 2009, for the 65th anniversary of D-Day, a group of enthusiasts and engineers attempted to recreate the Panjandrum. They built a replica, powered by modern fireworks instead of cordite, and launched it on the same beach. In a fitting tribute to the original, the replica also lost control, veered off course, and disintegrated, proving that the physics of the design were fundamentally, hilariously flawed, regardless of the era. The beach at Westward Ho shows no scars of the violence of 1943. The golfers play on the Royal North Devon course, unaware that 70 years ago, a 10-ton wheel of fire nearly assassinated the Admiralty's top brass on the very edge of their fairway. The Panjandrum exists now only in grainy archival footage and in the collective memory of British military eccentricity. It is a ghost in the machine of history, a reminder of a time when the desperate need for a solution outstripped the limits of engineering sanity. The story of the Panjandrum is, at its core, a psychological study of the Directorate of Miscellaneous Weapon Development. How could intelligent men, scientists, authors, career officers, convince themselves that such a contraption would work? The answer lies in the unique pressure cooker of 1943. Britain had been fighting alone for years. The fear of the Atlantic Wall was total. The DMWD operated in a culture of permitted madness. Neville Shute Norway later wrote that the department functioned because it was allowed to fail. In a conventional military hierarchy, a failure like the Panjandrum would end careers. In the DMWD, it was simply Tuesday. This freedom to experiment, to pursue the absurd in the hope of finding the brilliant, was a strategic asset. For every Panjandrum that crashed, there was a hedgehog mortar that sank a U-boat or a Swiss roll that landed a truck. The Panjandrum was the manifestation of the just do something philosophy. It was better to build a rocket wheel and fail than to sit in Whitehall and say the wall was unbreakable. The laughter that accompanied the project's demise was a release of tension, a recognition that they had pushed the envelope until it tore. The Weasers and Dodgers represented the best of the Allied war effort. A refusal to accept the impossible, even if it meant looking ridiculous in the process. The final after-action report on the Great Panjandrum offers a verdict that is both damning and affectionate. Mechanically, it was one of the worst weapons ever conceived. It had zero accuracy, zero reliability, and a 100% probability of endangering friendly forces. It was a weapon that fought its own user. A 10-ton unguided missile on a crowded invasion beach would have been a disaster of friendly fire. However, strategically, its existence was not in vain. It served as a definitive proof of concept for what not to do. It forced the planners to abandon the dream of a magic bullet for breaching the wall and commit to the hard, practical work of specialized tanks and combat engineers. It may also have played a role in the great deception of Operation Fortitude, signaling to the Germans that the Allies were obsessed with the heavy fortifications of the Pas-de-Calais, distracting them from the Normandy beaches where the real breach would occur. The Panjandrum stands today as the ultimate monument to the mad scientist era of World War II. It reminds us that innovation is a messy process, littered with failures. It teaches us that in the face of an existential threat, the human mind will explore every avenue, no matter how strange. The wheel stopped rolling in 1944, but its legend rolls on, a fiery, spinning testament to the audacity of hope and the unforgiving nature of gravity.